All right, so we're going to use the same example where we calculated the equilibrium constant of ammonia to be 130. All right, so we'll be given that piece of information. And now we're going to use a different set of conditions and ask ourselves what's going to happen in that case. And so in the previous example, we had the final concentrations, so we knew hydrogen was increasing. But in this example, we're not going to know one of the final concentrations. Instead, we're given the equilibrium constant, and we're going to solve for the final concentrations. Okay, so notice I have not put in the signs for the ice table change line yet. They have to be opposite, but I don't know if these are going to be negative and that one positive, or the opposite, if these will be positive and this one negative. So one thing we can actually do is calculate something called the reaction quotient. Okay? So the equilibrium constant is this ratio of the equilibrium concentrations. The reaction quotient is merely the same expression. Instead, we use the initial lines. All right, so let's pick a set of initial concentrations, calculate the molarities, and see what we're going to have. So this is 2 liters again, and we're going to start with 0.020 moles of nitrogen, 0.020 moles of hydrogen, and 0.12320 moles of ammonia. Very little ammonia is going to be present. So when we take the moles divided by volume, we get 0.010, 0.010, and 0.00010. All right. All well and good. We know the initial line. Let's go ahead and calculate now the reaction quotient from the expression for Q. So all we do is we're going to say Q is the same expression except now we put in the initial numbers, and it's going to be 1 times 10 to the minus 4 squared divided by 0.01 and 0.01 cubed. And when we do that, we're going to get Q equals, I think, 1. Okay. I'm back. I'm going to calculate Q and see what it is. So 1 exponent minus 8 divided by 0.01. 1. How about that? What a coincidence. Just happens to be 1. That means nothing in particular. It just means that these have just that, by chance, happens to be 1. Now 1 is less than 130. Okay, so let's write down, in this case, Q is less than K. Now let's think about what that means. If we have concentrations that give us a number that is less than the equilibrium constant, the reaction is going to want to proceed until the concentrations give you a larger number of 130. So in order to get a larger number, you need more in the numerator, and you need less in the denominator. So when Q is less than K, these are the signs you'll predict. Reactants should go down, products should go up, and we say that the reaction shifts to the right. Okay, so at this set of conditions, the rates are not equal. The reaction is going to be such that the forward rate is greater than the reverse rate, which means there's more reaction going this way than there is coming back. So that's going to build up. This is going to decrease. So I know the final answer is going to be larger than 0.0001, and these will be less than 0.010. And not only that, but when I solve for x, okay, so let's go ahead and write the expressions. All right, so we could go ahead and solve the equation 130 equals this squared divided by that to the first and divided by that cubed. That is algebra you do not want to do at all. But if I were to give you a series of solutions, it turns out that this mathematical equation is going to have 4 solutions for x. And only one of those 4 solutions will give positive numbers for the final answer. And so that's how you know what the correct answer is. So for example, let's just say one of the solutions, I'm not saying that was one of the solutions, but let's say one of the solutions was 0.02. Well, if you put 0.02 into here, you'll get minus 0.01. That's a negative concentration. That's impossible. So you say, nope, not allowed. So let's say another solution was x was 0.005. Okay, you put that into there, you get a positive molarity, good. You put that into there, and we get a negative number again. No good. No need to even check this one. And so now let's say, now the negative solutions should not be coming out because we've already determined that this is going down. So let's try another solution. See if it's reasonable. Let's say x happens to be, one of the 4 roots happens to be 0.001. That will be 0.009, and that will be 0.007. Both positive numbers. That would be okay if that was one of the solutions. And if you're given 4 solutions and this one gives all 3 positive numbers, you don't even have to look at the 4th one. Okay? The 4th one might be a negative number of some sort. All right, so that's how you use the reaction quotient to determine the signs of the changes that will give a positive number for x for one of the solutions that actually corresponds to the true equilibrium. So you should be able, if you've done this correctly, ignore the solutions that have a negative sign for x or even imaginary or complex numbers for x. You can rule those out immediately too.